Yeah, next topic is isocratic and gradient illusion. Illusion means that use solvent to as a mobile phase to carry the solute through the column, right? That the process is called illusion. But illusion can be done uh, as isocratic or gradient illusion. Isocratic illusion in Korean 등용매 용리, and in this illusion use only one solvent, yeah, or constant solvent mixture. One solvent means that only one kind, not only one kind, but you can have the mixture solvent like water and acetonitrile, right? But you don't change the solvent during the elution. Okay, that is called 등용매 용리, isocratic elution. Uh, but this elution uh, does not provide sufficiently rapid elution if all components are there. Okay, and in the meantime, gradient illusion. Yeah? Gradient means the slope, right? It is called in Korean the 기울기 용리. A continuous change of solvent composition to increase illusion strength. Yeah? This is often practiced in HPLC. So this gradient illusion is equivalent to um, temperature programming in gas chromatography. Okay, so this is open. Maybe in most cases, gradient illusion is employed. Okay, all right, and then now consider uh, these chromatograms. The purpose is to separate these eight uh, compounds by HPLC, but depending on isocratic or gradient illusion, the separation is really different. Okay, okay. Let's consider one by one. And here, uh, you will see how many chromatographs: one, two, three, four, five, and six, seven, eight. Okay, you will see eight chromatographs, and they are all different. The difference is the solvent. Okay, here it is the first one. Hmm? uh, it says 90% B. Here it doesn't say any A. A is aqueous vapor, B is acetonitrile. Here, so 90% B means 10% aqueous vapor, 10% is aqueous solution. Okay, and as you see here, uh, the separation is quite poor. Okay, and compound 1, 2, 3, and 4 uh, are not separated. Okay, and also 5, 6, 7, they are also not separated. 8, yeah, is a little bit separated, but the resolution is quite bad, right? So this one is not cannot be acceptable. Okay, but now let's increase um, the acetonitrile. Okay, and while decreasing this aqueous vapor. Okay, here this is much better than this first one, but still the compound 1 to 3 are not the separated. Okay, and then now let's keep increasing this aqueous vapor while decreasing the acetonitrile and the 70% acetonitrile. Here this one is better than the this one second one, but still compound 1 to 3 are not separated well, right? And then 60% the acetonitrile, and now this compound 1 to 3 begin to separate, but still very poor. But other compound, compound 4, 5, 6, and 8 are well separated. Still, compound 6 and 7, toluene and dimethyl toluene are not separated. Okay, and with 50% acetonitrile, oh wow, this is much better. with increasing retention time anyway, but still compound 2 and 3 and 6 and 7 are not well separated. Okay, but with 40% acetonitrile, this is much better. And uh, let's see, 30% acetonitrile, let me see, uh, well, this is 1, 2, 3. These compounds are well separated, and 4 also well separated. 5 also well. Okay, and other compound, compound 6, 7, and 8. They are separated, but this retention time is quite long, right? So this case, you see, cannot be acceptable, right? Because the analysis time too long, and this 35% B, this one this compound 8 is appeared, after a long time. So total analysis time is at least 2 hours. Okay, more than 2 hours, maybe 130 minutes needed. Okay. So from here, right, we know that um, uh, with uh, isocratic elution, separation may be done, okay, but it takes a longer time. You know, this one, more than 2 hours analysis time is not acceptable. You need a fast separation with good resolution, okay. So what can we do? By the way, reversed phase separation, Elution's strength decreases as the solvent becomes more polar. Okay. Anyway, this is the reverse phase separation. But from these experiments, one can draw a conclusion, which is that isocratic elution is not good in most cases. Okay, so one should do the gradient elution. Okay, here look at that. So up to maybe 7 minutes, use 30% acetonitrile, and then increase the percentage of acetonitrile, okay, and constantly, and from let me see, this is maybe 13 minutes to here, and 45% acetonitrile, and then still increase more acetonitrile up to 80%. Okay, this way, this is called gradient elution. Okay, but since it is segmented, this is called also segmented elution. Okay, it has 1, 2, 3 segments. In this part is the gradient elution. Okay, and with this elution programming, then here is the result. Okay, and within less than 40 minutes, all the compounds are well separated, okay, with very high resolution. Okay, now you see how gradient elution is better than isocratic elution. But here you have to decide, this programming. Yeah, the programming of elution is very important. Okay, as time goes by, solvent becomes less polar, so less polar solute comes out more quickly. Okay, so here the idea here is that you increase um, the this the acetonitrile portion, okay, relative to aqueous. Which means that acetonitrile is what, less polar than water. Okay, so this one, compound 8, this dimethyl methoxyphenyl, this is quite non-polar, the less polar. So this less polar, this compound is eluted. It is the retention time. Okay. Anyway, by increasing the acetonitrile portion, this compound 8 is eluted. much less time. Okay, and then your textbook introduces supercritical fluid chromatography. Okay, supercritical fluid. Yeah. This is called. It is one of the green technology. Okay, green means what? Environmentally friendly. Okay, this is green technology. Mm. That chemistry is called green chemistry, and green technology is really really important these days. So green technology, with green technology, we can reduce the contaminants. Yeah, we can what uh, there are 12 concepts of green technology. mm, and this is supercritical fluid chromatography is one of them. Okay, let's see. To understand this supercritical uh, fluid chromatography, you have to know what is the supercritical fluid. Okay, this chromatography is done using supercritical fluid. Okay, let's look at this table first. All right, and uh, well, yeah, this phase diagram first, and the phase diagram. Yeah, every what material has a phase diagram. This phase diagram is the plot, is the phase is plotted on the plane of pressure and temperature. Okay, usually x-axis is temperature and y-axis is pressure. Okay, depending on temperature and pressure, um, the material exists as a solid or liquid or gas state. Okay, for example, in the CO2 case, yeah, CO2 case, CO2 exists as solid CO2, the dry ice, yeah, um, below temperature here, yeah, and uh, at this pressure. Okay, in this area is a solid CO2. Okay, and then liquid CO2 exists in this area, and then other area the gas CO2 exists. Okay, and these lines now divide the phase. Yeah, and this one at this point the three lines meet together. This is called triple point. At triple point, uh, solid, liquid, gas state coexist. Okay, but important thing is that now look at this part. At a certain temperature, called critical temperature (TC), okay, and when temperature is beyond this critical temperature, however, in whatever pressure you exert, that liquid, you cannot uh, uh, make you cannot to make that gas into liquid. Okay, you understand, right? So this is called the supercritical fluid. Okay, yeah? Beyond this critical temperature. Okay, however, uh, you pressurized the gas. Yeah? It is not liquefied. Okay, this is but this is gas state. No, this is not gas state nor liquid state. But what's the state in this area? This is called supercritical fluid state. Supercritical fluid. Okay, this is not exactly gas nor a liquid. Okay, and supercritical fluid has a special characteristics. Okay, anyway, above TCA only one phase exists, no matter what the pressure. Okay, supercritical fluids can dissolve non-volatile solute. So this supercritical fluid has very special properties. Okay, for the supercritical carbon dioxide. Okay, and it displays special properties, uh, that is, it dissolves non-volatile solutes. Okay, It displays very special properties. And supercritical fluid, for example, uh, this what heat capacity is quite different from liquid and gas. Okay. Anyway, it displays very special properties. Okay. And let's look at this figure. There are several lists of compound: argon, carbon dioxide, sulfur hexafluoride, ammonia, diethyl ether, methanol, and water. Yeah, and so on. So the making supercritical fluid depends on this critical temperature. Okay, for example, carbon dioxide is very easy to make a supercritical fluid because critical temperature is a kind of very easily achievable temperature. Okay, and critical pressure is also uh, not very high. Okay, here. And critical density is like that. So to make the supercritical CO2, you have to increase the temperature beyond this one and increase the pressure beyond this pressure. Okay, so it's very easy to control. Okay, for the carbon dioxide and the sulfur hexafluoride also easy to make a supercritical fluid, but this one sulfur hexafluoride is not very inert. Okay, for carbon dioxide is inert material. Okay, and ammonia, you have to increase the temperature high and also increase the pressure. Okay, like that, right? So supercritical CO2 is the most commonly used supercritical fluid. So it is the industrially used to extract caffeine from coffee. Okay, one of the beauty of supercritical CO2 is to what? Uh, so in order to recover the CO2, uh, you simply the release the pressure. Okay, when pressure is released, the solvent turns to gas. Okay, very easy. Yeah, now you are here, and then you lower the pressure, and then this supercritical CO2 immediately becomes gas. Okay, leaving the solute in the gas phase for easy detection. Carbon dioxide is the supercritical fluid of choice, okay, for chromatography. So this supercritical CO2 is applied to chromatography to separate, not some compound. Okay, this is result. SFC is supercritical fluid chromatography. Okay, all these the compounds are rather easily separated by supercritical chromatography. Okay, this is now is the open tubular capillary column is used. Okay, and temperature is at for 140 degrees C. Okay, and density gradient was made by increasing pressure. Okay, in this case, increasing by pressure, the density gradient of a supercritical fluid was made. Okay, yeah, look at that. Yeah. All these compounds are very easily separated. Yeah, and this x-axis is not is a time. Okay, and this time since the this liquid supercritical fluid is pressurized, and then this time is also corresponding to the density of a supercritical fluid. Okay, mm? From low pressure density to high density. Okay, so this is supercritical fluid chromatography. So increased makes the separation time faster, increased speed and resolution. You can look at that. They are, where the closely spaced, but separation is good because of higher diffusion coefficient of solute. Yeah? This solute not solved in supercritical CO2, and this diffusion coefficient is higher. The low viscosity of a supercritical fluid also permits faster flow to increase productivity. Okay? Though CO2 is a weak solvent by itself, when mixed with some organic solvent, it is capable of dissolving a variety of compounds. Okay? Packed columns or open tubular columns could be used. In this case, open tubular column, capillary column is used, and with this supercritical CO2 as solvent. Okay, this is widely used, especially to extract coffee, the caffeine from coffee. That's how the decaffeinated coffee is made. Okay, okay, let's stop temporarily here.